first, okay, thank you very much for the organizer of this seminar. So I think it's a very good idea to organize such a such a seminars on this very interesting topic. So my talk, okay, will be divided in two. So I think, okay, I will have only the time to present the first part of my talk because I was, as usual, maybe too ambitious. So the first part will be a joint work with, in fact, one PhD student and a postdoc. So Yazid Janati, which is a postdoc of Eric Moulin and mine, and Badr Moufad, which is a PhD. And okay, for more senior colleagues, so Eric Moulin and Jimmy Olson from KTH. So what this talk will be, what is in fact the problems I'm interested in this first part of the talk. So here, in fact, I want to solve a Bayesian inverse problem. So what is in this type of problem at hand? So here I have some observation, let's say, which I denote by y here. And I'm supposing, okay, and here, in fact, it's somehow a very simplistic assumption, but okay, it's already gathered a lot of interesting models that this observation is a transformation of a signal X, okay, which is a signal of interest. Okay. So, interest plus, okay, and Z is some extra noise. Yeah. And okay, to complete, in fact, my probabilistic model, so here I need to specify, since I'm in a Bayesian setting, I need to specify the prior distribution on X. And here, okay, I specify that I denote my prior P0. And now the goal is, okay, based on my observation Y and the information of my prior P0, I want to reconstruct X. And just, okay, to give you a kind of a flavor, okay, very particular example, which in fact encompass a lot already of interesting problem. In fact, is the case where the transformation A is simply linear. And in this case, okay, I will give you a lot of problems appearing in image processing, for example, where okay, A is simply a linear operator. Already, in fact, brings a lot of issue. Okay, reconstruct the original signal X. So here, okay, I taking a Bayesian approach. So I specify a probabilistic model of my signals, and here the based on this probabilistic modeling. So it's specified here if I take for Z simply a Gaussian distribution. Okay, it specifies the likelihood of my model, which I denote here by G0. Okay, it's simply a Gaussian density with the right mean, okay, AX and the covariance sigma Y. And based on this likelihood and the additional prior, okay, it gives me the joint models, Px of Y, as simply, okay, the product of my likelihood and my prior distribution pi z. So here I'm supposing only a Gaussian noise, okay, for the inverse problems that I want to consider, but in fact, you can adapt the method that I'm talking about here to more complicated noise, in particular Poisson noise. Okay, but yeah, okay, just for sake of clarity, I'm just supposing a Gaussian perturbation in my observation. So that's the general problem that I want to consider, the general setup. And here, okay, I want to consider, in fact, another assumption in this setup. Here, the goal is to consider the case where P0, my prior, is a generative mode. And in particular, a diffusion mode. So here I'm supposing that I have a pre-trained diffusion model and I use it as a prior to solve my inverse problem. All right. So now that I have set up, in fact, the setting, so whatever, in fact, if P0 is a generative model or not, okay, the general goals to reconstruct my signal in a Bayesian setting is to sample from the posterior distribution, which is proportional to my joints, okay, simply by 0, x, y, okay, is simply my posterior, and which I want to sample from. And here, okay, it's as usual, okay, is a product of my likelihood and my posterior. Here, the main computational difficulty which I want to address is that P0 do not have a closed form density. So you cannot use, in fact, let's say traditional MCMC algorithm. So you need, in fact, to use some kind of adaptation. And yeah, in fact, I will present, okay, one common adaptation for a sample from this type of distribution and the extension. You can see, in fact, our method as a kind of extension of of a current. Okay, so here the general goal is really to tackle the problem of sampling from this type of distribution where, in fact, it is proportional to a known likelihood, G0 times a distribution which comes from a diffusion model. So here, in fact, one particular example, and I will give you, in fact, another other example in my numerical in the numerical illustration part of my talk. But here is a particular example where, okay, here I have an original image of a panda. I just noise it a bit, and if you use, in fact, let's say, pre-trained generative model, you can see that you have very clear image. Okay, you have the sample produced by your posterior are very clean. Okay, and sensible reconstruction of your original images. Okay, so that's okay. Just an illustration. I will come back to it later, or give you, in fact, provide you more illustration. So you could think, okay, at first glance that, in fact, since you deal with diffusion models, why not, in fact, try to use, in fact, or train another diffusion models? So that would be one solution which I just present here. So here, suppose that, in fact, you have some joint observation xi, yi, which comes from, in fact, the joint distribution, the joint distribution I just specified before. You could, in fact, think of approximating the posterior, okay, as also the marginal distribution of a diffusion model just by, okay, using the same terms which I will present in a few slides. In this case, okay, you need just to, in fact, take a parametric family of, define you a parametric family of likelihood, okay, parameterized by theta, and you can think of, in fact, minimizing the expectation of the Kullback-Leibler of the posterior with respect to the conditional. And just then, once you have trained and fit your parameter theta, you can just, in fact, take your observation y that you have, in fact, that you want to, from which you want to reconstruct the signal, and just simply sample from your trained models given the observations that you consider y. So in this case, okay, these options are two drawbacks or shortcomings. First, in fact, you need, in fact, to retrain your diffusion model, or even, in fact, train from scratch for any likelihood. So, which can be very computationally heavy. in particular that in fact you can think of that you may have faced a lot of different likelihood. Okay, so here there exists a lot of different inverse problems. So you can think that you have as many as inverse problems as the operators A that you can imagine. So you have in fact a very large amount of inverse problems that you would like to solve. And okay, here you wouldn't want in fact to solve and train a model for any inverse problem that you may consider. Okay. So that's why in fact training a model based on observation maybe not the most, let's say, efficient solution. And second, okay, here I'm supposing that I have access to joint observation xi, yi from my joint model. And in many situations, you may not have access to such observation. Okay? So think of the case where, in fact, the distribution that you may want to sample by zero, okay, again, is the product of the likelihood G0 times a model. The model um, is uh, is you can sample from the models, but you do not have access specifically the density or the distribution associated with your model is intractable. On the other hand, okay, G0 is provided to you. And one very famous example is if you train a reward model, in this case, in fact, G0 would simply be some exponential minus your reward. And in this case, okay, you cannot, just by the nature of the problem, you cannot have access to joint observation of your full model. Okay, so here, all in all, in fact, I do not want, in fact, to retrain I do not want to use at all neural network or train a neural network at least. So that's the option I do not want to consider. Here, I just want to use my likelihood and my pre-trained model. That's okay. So here, that's the goal which I want to achieve. Okay, that's so here's the main message that I do not want no further training of neural network. Okay. So just before, in fact, to present you one, in fact, very popular solution, which is posterior diffusion sampling, DPS. Okay, I just want to present the basics of diffusion models, which I need to present you DPS and the methods that we propose in our paper. So what is a diffusion model? So here I'm considering what I call the DDPM approach based on the paper by O and co-author in 2020. So in this paper, okay, the rationale behind diffusion model can be explained as follows. So here you consider first, okay, a joint distribution P0n, okay, and P0n consists in the joint distribution of Markovian models from x0 to xn. So x0, in fact, you start your Markov model, your Markov chain here by the data distribution P0. And then, okay, you just gradually, in fact, noise your original distribution, your original sample, okay, by a very simple transition kernel. So here we are considering as in the DPM a simple Gaussian transition. So here a Markov chain basically is just, in fact, I start from my data distribution and I'm considering, in fact, the Gaussian increment. So it just corresponds you can see this either as a simple autoregressive models or a discretization of an Ornstein-Uhlenbeck process. All in all, what is important is I want to target, I'm considering the parameterization of my transition in such a way that, so here's the mean, okay, at step k is alpha k plus 1 divided by alpha k xk, and the variance is 1 minus alpha k plus 1 squared divided by alpha k square identity. Here, okay, the main parameterization is so that, in fact, I target the Gaussian distribution. So that, okay, you can really see this as a kind of accurate discretization of an Ornstein-Uhlenbeck process. Okay, so here now I have a path from other distribution to the Gaussian distribution. Yes, but okay, if I want to define a generative models, I would like to go the other way around. I would like to go from xn to x0. And so that's why, in fact, and since I'm considering a Markov chain, just by using Bayes formula, I know that, in fact, if I'm looking at the Markov chain backward to xn to x0, I know that it is also a Markov chain with initial distribution, the marginal stage n of my original Markov chain, okay, so Pn xn, which I know is just by construction approximatively Gaussian. And then, okay, the product of the conditional distribution of xk given xk plus 1. However, yes. So now, so here, so the main component is the backward process. Okay, so now we can consider always the backward process. Okay, it's somehow an ideal generative models, which is Markov chain starting from the n iterates of my noising process and going backward. But the main issue here is that, of course, the conditional distribution from xk given xk plus 1 are intractable, okay, because they are proportional to the joints, and in fact, the joint, you do not really know the joint because you do not even know exactly the marginal of the forward. So here, the main issue in this framework is how you can, in fact, get access to this backward transition, pk given k plus 1. And here the solution is, okay, simply try to approximate it. Try to approximate them. So to this end, okay, so here I will consider a very simple target, a simple approximation, and here I take even a variational inference approach, and I'm taking as approximation of my unknown conditional Gaussian transition. Okay. So here I'm supposing that the approximation I consider for pk given k plus 1. So here it's a transition parameterized by theta, is a Gaussian, okay, with mean, okay, with the mean and variance parameterized by my parameter theta, and which take as input xk plus 1 and sigma xk plus 1. So in this case, it is, so if you now consider the Kullback-Leibler divergence between my joints, my ideal joint, and my the joints associated with my backward, okay, where in fact I'm supposing that for my approximation, but it does not really change anything, that my original Pn theta is simply the Gaussian. So here, if you now compute the Kullback-Leibler between the two path distribution, which of course upper bound the likelihood of my data with respect to the marginal of my model. So this Kullback-Leibler divergence can be decomposed as a constant which does not depend on theta, and the sum of an expectation under pk plus 1, okay, so where pk plus 1 is the k plus 1 marginal of my ideal models, which I, in fact, can simulate if I have some data, of the Kullback-Leibler divergence between the two conditions. So in this case, if I took this Gaussian parameterization of my approximation of this conditional, I know that, in fact, I have somehow a closed form solution for the mean and the covariance matrix. I know that the optimal parameter corresponds to the expectation of xk given xk plus 1, and for the covariance is, of course, okay, the conditional covariance matrix. So here, what DDPM, in fact, approximates, okay, shows approximation. So learning the covariance may, in fact, be a bit too computationally demanding. So here, what you consider in the DDPM approximation, you consider here simply you use, in fact, the form of the conditional expectation and the covariance as follow. You know that, in fact, the conditional expectation can be written as simply as a linear combination of xk plus 1 and eta k plus 1 dk plus 1 xk plus 1, where dk plus 1 is what is called a denoiser, meaning the conditional expectation of x0 given xk plus 1. And the covariance matrix, okay, has a kind of similar structure, but here, in fact, you can show that it is simply a known matrix, which is a scalar times the identity matrix, which is explicitly known. Plus, okay, some scalar, okay, which is also completely known, the covariance matrix x0 given xk plus 1. So here the idea in DDPM is that, okay, based on this decomposition of my ideal approximation, the best Gaussian approximation that I could dream of, I will take the DDPM parameterization of the mean and the covariance consists just in fact, follow the exact same structure for the mean. Okay, so here I'm supposing that, in fact, I'm parameterizing the mean as gamma k xk plus 1 plus eta k d k plus 1 theta xk plus 1. Okay, so and here d theta k plus 1 will be a neural network. And for the covariance, I just drop the covariance of x0 with respect to xk plus 1. Okay. And I just, okay, suppose that my approximation of my covariance is the known scalar which I can have access to. It's completely known, the identity matrix. Okay. So in this case, okay, so if you do, in fact, this parameterization, what you make for as approximation for the conditional distribution of xk given xk plus 1 is simply, in fact, equivalent of taking the bridge, okay, of your original Markov chain, okay, of xk given x0 and xk plus 1, and you take the conditional bridge, but you specify, in fact, the conditional bridge. You just change the conditional bridge x0 with denoiser applied to xk plus 1. Oh, so that, in fact, gives you the parameterization that you can that's Owen co-author have proposed to approximate the conditional distribution of xk given xk plus 1. Okay. And if you plug, in fact, this approximation in the decomposition of the Kullback-Leibler divergence as just present you, in this case, if you do simple algebraic manipulation, you can resort that, in fact, training your neural network is just boils down training your sequence of denoiser parametrized by theta. Okay, so all in all, in fact, the main message here is training diffusion models is just training the sequence of denoiser I just introduced before, and now based on the sequence of denoiser, it defines, in fact, based on the relation between the parametrization of the mean in my Gaussian approximation and the denoiser. It gives me, specify automatically the approximation of the Gaussian transition I consider, and then it specify directly the diffusion models that I have been trained off. Okay. So I just want also to recall, in fact, because it is really well known that in fact you have, by 2D formula, you have a well-known relation between the denoiser and the score of your ideal diffusion model. So you can show that, in fact, if you consider the score of your ideal diffusion model, meaning the gradient log of the margin at step k, for k equals 1 to n, you can relate this score to the denoiser by the following expression. And so, in fact, learning a sequence of denoiser based on this relation is equivalent to learning a sequence of score, okay, approximating the sequence of ideal score of my original noising process. Okay. So here I will be using, in fact, these two types of these two viewpoints of diffusion models. So that's why, in fact, I need to introduce both of them, because, okay, it's very convenient to go from one to the other from time to time. Oh. Also, I want to recall, in fact, the main philosophy, okay, which summarize a bit what diffusion models perform. In fact, so here I'm just recalling that, in fact, the conditional distribution, you can write the conditional distribution of xk given xk plus 1 as the marginal, okay, of the joints of xk and x0, okay. And here, if you write the joints of x0 and xk given xk plus 1, you can write it as a product just by Bayes' rule. You can write it as a product of the bridge, meaning the distribution of xk given x0 and xk plus 1 times the conditional of x0 given xk plus 1. So here, making, in fact, the approximation that is conditional is approximatively the bridge where you replace x0 by the denoiser. Here, in fact, you can see that in the approximation of that is done in diffusion models. In fact, the approximation that you do in diffusion models that just consists in replacing the conditional distribution of x0 given xk plus 1 by the Dirac mass at the denoiser applied to xk plus 1. Okay. So that's, in fact, an approximation. Okay, you can really summarize somehow all diffusion models using this approximation. And here, in fact, in the method that I will present you, in fact, this approximation will be also performed. Okay. So here comes, once, in fact, I have introduced you all the tools that I need to introduce you posterior diffusion models. So here, in fact, I want to, in fact, ideally, I would like to consider or approximate the diffusion models for which pi 0y is the final target distribution. Okay, without training new models. Okay, that's the challenge. And here, what I would like, okay, if you just by definition and the presentation I gave you about diffusion models, yeah, I would like
somehow to have access to a sequence of denoiser associated with the diffusion models for which the initial distribution is not P0, but is my posterior distribution, which is a twisted distribution associated with P0, which I denoted by P0y. Okay. So here, this sequence of denoiser, which I would like to have access of, is just by definition is the as I said before, the denoiser is simply, in fact, the conditional expectation of x0 given xk. Okay, and here, you can write it simply with the notation I introduced to you. Is just by definition of the conditional expectation is the integral of x0 with respect to the conditional distribution of x0 given xk. But where x is the conditional distribution of x0 given xk, this time is not proportional to P0 times the transition density of my original noising. This time, I just replace P0 by my true target, which is my posterior pi 0y. That's in fact the sequence of denoiser which I would like to have access of. And if I would have access to the sequence of denoiser, I would be in fact able to simulate the diffusion model associated with pi 0y, and so I would be able to sample from my posterior. In the same, in the same spirit, as I was saying to you, getting access to the sequence of denoiser is exactly the same as getting access to the sequence of associated score, of my diffusion models, not starting from P0 this time, but of pi y, and that's exactly the same story here. Alternatively, to my sequence of denoiser dky, in fact, ideally, I would like to have access to this sequence of score associated with a noising starting from the posterior. So now, in fact, if the questions that you may wonder, and that's in fact paper try to solve, and us as well, is that can you get, in fact, since in fact here you have access to the sequence of denoiser of my original diffusion models, which is used as prior and my posterior. You also have access to the sequence of core associated with this diffusion model. So the question that you may wonder is that this sequence of score p gradient log p ky, is this function can be expressed as the score of my original diffusion plus something, and this something can I approximate this something. And turns out that in fact it's almost you can almost do it. So here if I'm denoting pky xk is the marginal of my diffusion model starting from my posterior here. In fact, if I play a bit with Bayes' rule, and here are all the details, you can write in fact the marginal associated with my ideal diffusion model starting from my posterior. You can write this sequence of marginals, as the product of, let's call it a pseudo likelihood gk of y given xk times the marginal of my original diffusion models used to define my prior distribution. So here, all in all, you can write it really for any k. You can write pk y as up to proportionality as the product of gky given xk and pk xk. And now, if I use again the 2D formula and the relation between the denoiser and the score. Here you can remark and observe that the sequence of denoise, the denoiser which I'm looking for, dky, is in fact a linear combination of my original denoiser, dk xk, plus, okay, the scalar times the score associated with my pseudo likelihood gk. So since in fact I'm using a pre-trained diffusion model, so I know that in fact dk xk can be, I have access to at least approximation of dk xk, okay, as dk theta xk. But the main issue here, the main problem that I face on is that the score associated with the gk are intractable. Why so? Because here, just by definition, from what you can see here, the gk are integral. And in fact, they are integral, they are high-dimensional integral that you can, in fact, not estimate efficiently. And so here you need to come up with let's say well-motivated approximation. And that's where, in fact, DPS comes in. And here, the idea is to use, in fact, the same type of approximation as DPM. Okay. So here, the idea is to looking the pseudo-likelihood GK in the eyes. Here, you can write, in fact, the likelihood, the pseudo-likelihood at iteration k. You can write it, as I was saying, as the integral of my original likelihood, my observation given x0, times, in fact, the conditional distribution, the conditional density of x0 given xk, and here the conditional distribution, because the conditional density is with respect to my original pre-trained model. So here, based on this observation and keeping in mind, in fact, the approximation that you make in the DPM, here you can make the same approximation, meaning you can approximate this conditional distribution of x0 given xk as the Dirac mass at the denoiser at step k. Okay. And so doing so, we have what I call GPS approximation, okay, which have been proposed in this paper here. And here you can now, okay, if you plug, in fact, this approximation in the definition of the GK, you have, in fact, an approximation of the sequence of denoiser associated with the diffusion model starting from the posterior, and you can use, in fact, this approximate denoiser to get approximate sample from the posterior. Okay, so that's one option. Okay, and okay, I will spare you the implementation details. That's okay. Of course, you need to, let's say, rescale properly the gradient if you do not want, in fact, the algorithm to diverge too quickly. So now, in fact, here comes the methodology we come up with my colleagues. So here's the main observation that we make, in fact, and what we try to improve DPS approximation is that if you take a look on the approximation that you make here, we make the approximation that the condition distribution of x0 given xk of my original pre-trained models is a Dirac mass. Okay. And here, in fact, you can, okay, if you know a bit about diffusion model, and in fact, if you think about the forward noising process, this approximation, in fact, is relatively okay if the step k is relatively close to 0. Okay. So here, the observation which I would like to use, and that we use, in fact, is the method I will present you, is that, in fact, I want to use this type of approximation for iteration which is close to 0. So that's the first observation that I will be using here. And the second one, okay, is that, okay, in DPS, I use, in fact, one expression for GK, whereas, in fact, if you play a bit with the expression of the GKs, you can, in fact, come with k-1 expression for the GK as integral. So here you can always express for any L smaller than K. You can, in fact, always, express GK, the pseudo likelihood at stage K, as the integral of the pseudo likelihood, okay, at stage L, times the conditional density of my original pre-trained models of xk given xk. So here, now, based on this expression for the GK, and I can in fact use the same approximation of I can plug in fact in this integral the DPS approximation for the GL for any L, and based on, if I plug in this approximation, I obtain in fact L of K minus 1 a new approximation of the GK, and here I denote them G at KL. So here for any L and for any K, okay, for any L and K, L of course smaller than K, GKL, K is an approximation of the GK. Okay, so that's the second observation that I want to use, and I will combine, in fact, these two observations to come up with a new sampling algorithm to sample from my posterior. So here, the sampling algorithm which I will try to I will come up with, in fact, will do the following. So what I will consider, what I will try to sample from iteratively and recursively, is that I will try, in fact, to sample backward the sequence of marginal of the diffusion models which initial distribution my posterior. So here I'm defining PK. PK corresponds to the marginal of my diffusion model starting from my posterior. Okay, and here, just by definition and with all the story I just explained you, in fact, this sequence of marginal, if you recall, in fact, which I told you, is simply like the product of my pseudo likelihood at stage K and the marginal of my original diffusion at stage K as well. Okay. So here I would like, so here's the method that which I will come up, is in fact trying to sampling approximatively sequentially this sequence of distribution pi k. Okay. Given that now, okay, pk I can simulate easily, in fact, pk, and I have, in fact, the corresponding denoiser, and okay, I have k minus 1 approximation for the gk. Okay, so based on this, so since I have L minus 1 k approximation of the gk, I have also, in fact, just by definition of the pk, I have also k minus 1 approximation of my marginal, pi k, which I denote here by pi at lk. So here I consider pi at lk as the distribution which is proportional to my approximation of the gk at L times pk. And now, okay, I want to combine all this approximation of the pk. Okay, and here, okay, to combine all this approximation, I just consider, in fact, a mixture. And here's the approximation of the pk I'm considering at the end is simply a mixture of the pk at L, okay, with some weights, okay, wkl, which sums to 1, of course. So now, okay, I have, in fact, a sequence which is supposed to approximate my sequence of pi k, which I want to target. And now the idea that of our method is to use, in fact, to try to sample to this sequence of approximate marginals. So how to sample from these approximate marginals? Here, here we take, in fact, what we call the data augmentation approach, or if you are familiar with Gibbs algorithm, in fact, it's simply a Gibbs algorithm approach. So the idea is, okay, first, okay, I want to sample from this P at KL, okay, and I want to sample them, okay, this sequence of distribution recursively. So suppose now that I have a sample from P at K plus 1. I want to get an approximate sample from P at K. Now I sample first the index L, okay, in my mixtures according to the usual categorical distribution. And once, in fact, I have sampled my LK, so here I dropped for notational simplicity the index K in L. Here now I want to sample from this P at KR, which is a product of G at and PK. And here the main observation is that, in fact, this marginal distribution can be written as a marginal of a joint distribution over x0, xk, and xl, which I denote here by P at 0 lk. And this joint distribution is a product of my transition from x0 to xl, okay, which is simply a Gaussian transition here. No, sorry, it's the condition distribution of x0 given xl of my original diffusion, which in fact I can sample from, time my the approximation of my pseudo likelihood G at L, and the product of the conditional distribution of xl given xk, which in fact I can also simulate relatively easily. So that's in fact the margin, the joint which I consider, and okay, it's relatively easy to show that in fact if you marginalize the joint with respect to x0 and xl, you obtain the approximation P at KL that I just introduced to you. So now now based on this observation, you can make use of a Gibbs sampling approach, trying in fact to sample in fact this joint distribution by sampling from the conditional distribution associated with, and just keep in fact the case marginal associated with this sampling. So here, of course, in this Gibbs sampling approach, I will initialize, of course, the xk by my previous sampling at iteration k plus 1, x at k plus 1. Okay. So here I will specify what's in fact what is this Gibbs sampling which we can use. Okay, because here now I need to specify the conditional distribution of the joints I just found. So here, if you just use the Bayes formula, as usual, you can find relatively easily the sequence of conditionals that you want to sample from to use them in a Gibbs sampling, in the Gibbs sampler. So now if you consider the conditional distribution of x0 given xl and xk, you just obtain by definition the conditional distribution of x0 given xl of your original diffusion model that you can sample from efficiently because you have a pre-trained model. So that's easy. Now, okay, I will skip the second term for the moment and go to the final one directly because it is also an easy conditional distribution. So here I'm considering the distribution of xk given x0 and xl. And in this case, in fact, it's simply the conditional distribution, the noising, in fact, the conditional distribution associated with the noising, meaning the conditional distribution of xk given xl, and this is simply a Gaussian distribution here. And now, okay, so you can see that the first and last conditional you can very easily sample from, but the main problem now is for the second one. which in fact is known up to a normalizing constants and which are in fact intractable. Okay. And so to perform in fact this step, okay, so here to approximate this conditional, so here we just take a variational approach and we consider in fact at each iteration we consider a Gaussian approximation. So here parameterize, okay, we just take some mean, okay, and some covariance mu phi L and sigma L. And at each iteration in my Gibbs sampler, I will approximate, okay, the conditional which are intractable, okay, by this Gaussian approximation. I will optimize over the parameter phi. Okay. So all in all, okay, the Gibbs sampler works like this. So given now x0r, xlr, and xkr are, for which in fact I want to target the joint I just showed you before. So first, I perform a few gradient steps to get a variational approximation of the conditional which are intractable. Then based on the parameter phi, I estimate, I sample, in fact, an approximation of the conditional based on the resulting Gaussian approximation. And then, okay, for x0 and xk, since the conditional are explicitly known, I can explicitly sample these two conditional. And then, okay, I'm proceeding recursively on R. Okay, so that gives us, in fact, the full pipeline, okay, our full algorithm to get, in fact, now an approximate sample from the marginal of the diffusion model, on which, in fact, you initialize not by the data distribution, but to you initialize with the posterior. Okay. Just to give you a few details about the Kullback-Leibler minimization procedures in the Gibbs sampling, in our Gibbs sampler. So, in fact, the Kullback-Leibler divergence between, in fact, a Gaussian approximation and the conditional at ends, you can, in fact, write it in a relatively explicit form, and using parametric reparametrization trick, you can write, in fact, this the corresponding loss function associated with, okay, this the minimization of this Kullback-Leibler with respect to the parameter phi. You can write it up to an additive constant which does not depend on phi as, okay, an explicit term here, which corresponds to the Kullback-Leibler of two Gaussian distribution. So here you can explicitly, in fact, compute the second term here, because as I was saying, okay, it's the Gaussian of between two known Gaussian distribution. And for the first term, okay, which corresponds to the expectation of the log likelihood, but taken at the denoiser, you can in fact get Monte Carlo NBS estimate of this term, and all in all, you can use stochastic gradient descent to minimize this loss function at each iteration. Okay, so the main message here is that, okay, you have, in fact, you can the minimization step inside the Gibbs sampler that we consider can be performed relatively efficient. Okay, so
we have a quick question in the chat. Sorry. So
yes.
Dora
Yes.
Louis asks, is there a typo in the second line? This is.
So where is the typo? Let me see. Okay, well, is in the second line? Which second line? So here, where is the typo? Sorry, page 24. Okay. So,
I was.
So where is the? Let me see. So where is the typo? What do you think? 26, sorry. Where is the typo? So here it's k given L, 0 given L. I think it's fine. And what do you think is where do you think is the typo? So,
Dora, I'm allowing you to talk.
For the second line, why it is QL 0K, XL given X0 and XL instead of XK?
so it's XK, yeah, of course. Yeah. You're right. Thank you very much. I need to correct to make the modification. Any other question?
No question.
Thank you. Thank you very much. Oh. So yeah, so to conclude, maybe some questions that in fact you can wonder is that okay, why not simpler? Because here in fact I'm at the starting of my Gibson. Before in fact I sample the index in my mixture before performing the Gibbs sampling, the Gibbs sampler. And in fact, you could incorporate the sampling of the mixture index inside the Gibbs sampler as well. But okay, so the simple answer is that it is very too costly to update the weights. In fact, in your Gibbs in the Gibbs sampler, if you incorporate the index, so that's okay, the first answer. The second question that you also may wonder is, okay, why not, in fact, consider a simpler data augmentation scheme? Because, in fact, you could proceed as before, okay, and use also Gibbs sampler just focusing on XL and XK. Here, the main reason here is that if you take a look on the line where there was a typo, right, you could in fact also only consider a joint over L and K and not in fact considering 0. But now in fact for the conditional, so the main step in the Gibbs sampler will be also the intractable conditional will correspond to the conditional distribution of XL given XK. But in this time, you wouldn't have, let's say, this particular form for the conditional. And here, like, what is the trick is you cannot, in fact, perform the variational approximation. If you take also variational approximation approach to sample from this conditional, it performs very badly compared to considering this the conditional of XL given X0 and XK. That's mainly because here, in fact, you have a known component in this conditional, which helps a lot in the training, compared to where you would have only the conditional of XL given XK. So that's for the second question. And the last one is, okay, what is the right choice for the weights? And for the right choice for the weights is that, okay, here we do not play a lot. So here we really, in fact, it was just some empirical evidence. And in fact, to not bother with fine tuning, we just took for our numerical experiment, we just took the uniform weights for the weights WP. Okay, so that's the overall method that we come up, and that's now the experiments. So we performed some comparison of our proposed approach with a bench of state-of-the-art sampling algorithm for the Bayesian inverse problems that's with the forms that we consider here, meaning with diffusion post prior. And so here, okay, we can see that our methods outperform the other one on most inverse problems that we consider. So here it's really only on image for image problem. And here are some sample. I will not come up to it. So here we consider, in fact, impinging problem, also JPEG problem, and super resolution inverse problem. So we have, in fact, we have tested our algorithm on a bunch of image inverse problems. So but just to conclude, we have also tried another application in audio, where we also consider inverse problem coming from a source of separation. So here you have a sound, which in fact is just a music track, for which in fact there is in fact bass, drum, piano, and guitar, and you want to separate. In fact, you want the sound coming from each of the instruments. So to do so, in fact, we take a very simple linear model. So here we have an observation Y, okay, which is supposed to be the sum of the signals corresponding to each of the instruments. And now we want, in fact, to reconstruct all the instruments. And so using, in fact, a known test data sets and a known generative models from Hugging Face, so all the details are in the paper. You can see that on this particular application, our method is very competitive to existing one. Okay, so that's conclude my talk. Okay, because I think I'm out of time. But yes, I will not be able to talk about the second part of my talk, unfortunately. But yeah, I think it's enough. Thank you very much for your attention.